Hello, my name is Rohan, and for my reflection, I would like to discuss the usefulness of the paper to the software engineering discipline by extending one of the most important analysis techniques, program slicing, for procedural languages to object-oriented systems. Classic slicing methods were built around procedures, global variables, and static call structures. But object-oriented systems introduces classes, objects, inheritance, encapsulation, and dynamic dispatch, all of which make slicing much more complex. The value of this contribution becomes clear in the paper's introduction, where the authors highlight slicing's role in debugging, testing, program understanding, reverse engineering, and metrics analysis, all on page 1. The paper shows how traditional system dependence graphs, SDGs, fail to capture hidden object-oriented dependencies such as interactions through instance variables and dynamically bound methods. The new object-oriented aware SDG model supports precise debugging, which can be found in page 1, paragraph 1 of the paper. And I quote, program slicing has many applications such as debugging, code understanding, program testing, reverse engineering, and metrics analysis. And here, in page 1, right column, is where the precision across polymorphic calls and calling context is indicated when describing the role of summary edged and the two-pass algorithms. And next, the new SDG model also supports program comprehension across class hierarchies, also on page 1, at the same sentence, and at page 1 to 2, where the paper specifically emphasizes inheritance, polymorphism, and interacting classes. Because SDGs support slicing across these inheritance-based structures, this directly enables program comprehension across class hierarchies. Other than that, the SDG model, the new one, supports modular analysis and reuse of class-level representations. It is stated here in page 3, the first paragraph of section 3.1, that, and I quote, to facilitate analysis and reuse, we represent each class by class dependence graph CIDG, and found here in page 5, section 3.1 under representing derived classes, and I quote, we construct a CIDG for a derived class by constructing a representation for each method defined by the derived class and reusing the representations of all methods that are inherited from base classes. Lastly, in slicing incomplete systems such as class libraries, the paper directly supports slicing of incomplete object-oriented systems in the abstract. And I quote, another advantage of our approach is that slices can be computed for incomplete object-oriented programs such as classes or class libraries. Also, the concept of a frame which simulates a universal calling environment for incomplete systems reinforces this idea. It is found here in page 6, first paragraph of section 3.2. This explicitly enables slicing even when the system has no main program. Because modern software is predominantly object-oriented, this work fills a necessary gap by making slicing directly applicable to real-world software engineering tasks. Now, the points I presented, motivation and problem statement, were derived directly from the paper's introduction and early conceptual sections. I analyzed the motivation by focusing on identifying why the authors thought they needed a new slicing framework. The introduction explains over here in page 1 that earlier slicing algorithms were designed for procedural languages and depend on SDGs that assume procedural features. Also, object-oriented features fundamentally break these assumptions. For instance, instance variables persist across method calls and are hidden from the caller. This creates an invisible data dependency. And finally, Throughout the introduction of the work, the authors explicitly state that earlier object-oriented slicing attempts were incomplete and lacked full coverage of object-oriented features. And these passages form the backbone of the explanation of why object-oriented slicing is challenging and requires new representation. Next, the problem statement emerges from multiple places. In pages 1 to 2, it describes object-oriented specific challenges such as instance variables, inheritance, polymorphism, dynamic binding, and encapsulation, all of which require new dependencies representations. Page 2 describes the author's goal, reusable and modular SDGs that can be combined for classes, interacting classes, and complete programs. And page 2 explicitly states the need for handling incomplete systems, where classes and libraries must be analyzed without a main program. I synthesize these elements to form a concise, clear problem statement describing what the authors aim to design: a reusable, scalable, object-oriented SDG representation that supports precise interprocedural slicing across all object-oriented features. Now, while in analyzing the motivation and problem statement, I encountered several challenges. Firstly, is the dense theoretical content. The paper assumes strong prior knowledge of procedural slicing, dependence graphs, and compiler theory. Concepts such as summary edges, parameter in and out vertices, and control dependence edges required repeated reading to fully understand what their implications in object-oriented contexts were. Secondly, is the visual complexity in diagrams. The CIDG and SDG diagrams, for example, figure 2 on page 4 and figure 5 on page 7, are extremely detailed, packed with multiple types of edges, control data parameter, and summary edges, and understanding how they demonstrate object-oriented specific problems required careful cross-referencing between the diagrams and the text. Thirdly is the interwoven discussion of motivation and solutions. Some motivational points appear mixed with solution details. For example, on page 2, the authors discuss object-oriented difficulties, but immediately transition to their proposed graph-based solutions. Separating problem from solution required deliberate attention. It wasn't just clearly stated. Finally, is understanding hidden dependencies. The idea that instance variables creates invisible data dependencies, which I said on page 2, was conceptually challenging. It required rethinking program slicing and not as statements affecting variables directly, but also through long-lived object states. Lastly is my own opinion on the work, the advantages and limitations. So let's start off with the advantages. Firstly, it is highly relevant to modern software. Since most real-world systems are object-oriented, extending slicing to object-oriented languages greatly increases slicing's practical value. Secondly, it is a modular, reusable analysis. The idea of constructing class-level dependence graphs, CIDGs, that can be reused across multiple contexts is a strong engineering advantage, which I state on page 2. It supports incremental development and reduces computational costs. Thirdly, it handles complete and incomplete systems. The frame-based approach, which I state on page 6, is an elegant solution for analyzing class libraries before they are used in application. Very practical in modern development workflows. Lastly, it preserves precision across polymorphism and inheritance. Dynamic dispatch is notoriously difficult to model statically, And the polymorphic choices vertex approach is both intuitive and theoretically grounded. Now, as for the limitations, my opinions are that the high complexity in representation size, although the authors provide upper bounds and argue that in practice the graphs are smaller, which are stated in page 9, SDGs for object-oriented systems still risk becoming extremely large and source-intensive. Next is the limited support for dynamic language features. The paper focuses on statically typed languages like C++ and Ada95. The technique may not translate cleanly to highly dynamic languages like Python or JavaScript. Next is that it assumes perfect alias and type analysis. The paper acknowledges in page 6 that precise type inference for dynamic dispatch is NP-hard, which limits the precision of polymorphism slicing in real systems. And lastly is the steep learning curve. Developers without background knowledge in program analysis may find the graph representations and slicing semantics difficult to understand or adopt. And that is all. Thank you very much.